Let's introduce a couple of very powerful, important relationships about angles inside of a triangle. The first one is about the interior angles in a triangle. Now, by this stage, actually, most students already know the fact that if you've got a triangle, that the three angles add up to 180 degrees. Now, I'm going to prove that in just a second, but an informal proof is just to rip off the angles and put them together. Now watch what happens if I take this angle and put it with this angle, as best as I can. And if I put it with this angle, guess what happens? 180 degrees. Do you see the line that got formed there? That actually worked better than I thought. All right, another way to think about this or to prove it is to take a triangle. We'll call this triangle ABC. I'm going to number these 1, 2, and 3. Now, you and I want to prove that 1, 2, and 3 add up to 180 degrees. I'm going to do some work over here. The given is the triangle here, and also in the given, here's the little trick to this proof. Watch, I'm going to create a line that is parallel to this one. So, given triangle ABC, that was given, and we're given that BD, line BD is parallel to AC. So we just created a line that would guarantee parallel there. Now, watch what happens. We want to show that a 1, 2, and a 3 all add up to 180. So let's do a little bit of work here. Let me call this angle 4, and I'll call this angle 5. We know that this angle and this angle are equal to each other. The measure of angle 1 equals the measure of angle 4. Parallel lines give us alternate interior angles that are equal and congruent. It would also be true that 3 and 5 will be equal. So measure of angle 3 equals the measure of angle 5. Parallel lines give us alternate interior angles that are equal. Now I want you to notice something here, that the measure of 4, the measure of 2, and the measure of 5 all equal 180. They basically form a straight angle. We're pretty close there. Look, 4, 2, and 5 equals 180. We want 1, 2, and 3 equaling 180. But I think you can see what to do right away. We notice that a 4 is here and a 5 is here. But look, 5 is the same as a 3. And look, 4 is the same as a 1. So what did I do? I did 2 substitutions there. And I have my all-important theorem that the three angles inside of a triangle always equal 180. Now, there are a lot of questions that come from this that you can work on, and they become fun little puzzles. You know, it could be as nice as this. This is 110, this is 40. So they'll say, how big is this angle? So 150, this makes this 30. Right? Something like that. They might expand your knowledge a little bit here. Something like this. Let's see. Give us 120 here. They'll want to know this angle and this angle. And they'll tell us that this is 75 and that this is 70. So, I don't know. Let's try this one out. So this is 145. That leaves me 35 for this angle. Okay, I can do that. 180. Vertical angles are equal, so now I'm over here, I'm at 155, and so the last angle is 25. Lots of things you can do. This little theorem shows up everywhere because it's so important, the angles in a triangle. The second angle relationship I want to talk about is that the base angles of an isosceles triangle are equal. Now, before we do anything with this, we got to get some words out of the way. When we talk about an isosceles, we know it's defined by a triangle with at least two equal sides. So if these are the sides, these are called the legs of the isosceles. Those are always known as the legs. The congruent sides are always the legs. The side that is not our partner's there is known as the base. Now, we're going to try and prove that the base angles, these two, have to be equal. And I'm going to do it in a little bit different way. You could do a couple of things here. You could split this down the middle and do kind of a congruence proof, but I'm going to go all the way back to symmetry. You and I learned that an isosceles triangle has a line symmetry, one line symmetry. And what that actually would mean about this line of symmetry is that this would match this, that this angle would have to be the same as this angle, that this piece must match this piece, and it would also mean that this angle must reflect onto this angle. So there's my informal proof that through a property of symmetry that those base angles must be equal. Now this creates all kinds of great questions. I can give you an angle of 40 here and ask you this, and you say, how do you do that when you only have one angle? Normally we need two. But guess what? These have to be the same. So 180 minus 40 is 140. Divided by 2 makes these 70 each. That's kind of cool. What about if I give you a base angle in an isosceles? So let's say that this is 20 here. How do you find this angle? Well, base angles are equal, so this would be 20. That makes this 140 up here. Now there are lots of good problems that come from this. Let's see if I can quickly make one more up. Let's see here. I like the ones that kind of do this kind of thing here. Let's see. Let's put in one number. Let's see how we do. Let's say this is 50. Now, pretend that that's a straight line. Let's redraw that so it's straight there. Okay. I think from that 50, I could get every angle in this diagram. Let's see. This is 50, so 180 minus 50 is 130. So these are 65 each. Now, this is a supplement, a linear pair, right? So this is 115, right? 70, yeah, 115. Now, how much does that leave us left over? So it leaves us 65 left over. So we have to take 65 and divide by 2, which would make this 32 and a half and this 32 and a half, because this is also an isosceles, a poorly drawn one, but it is indeed. The last property that I want to talk about is called the external angle theorem, or the exterior angle theorem. And the way it works is if you have a triangle and you extend a side, so you just start continuing that as a ray, it forms what we call an exterior angle. So this is the angle in the exterior. Makes sense. Now there's some other names that get used in the theorem, so let's talk about them. These are obviously interior angles. This is the near interior, because it's the one that is the linear pair with the exterior angle. And these guys back here are known as the remote angles. A remote cabin means a cabin way out in the woods, all by itself. The remote ones are in the back corner of the triangle. Now, what is the theorem then? How does this work? Well, the theorem claims, and we're going to prove it, that the measure of angle 1, this exterior angle, is equal to the measure of 3 and 4, the two remotes. The exterior is equal to the two remotes. So let's give that a try. Let's see if we can prove that. So this is what we want to prove. Let's pull it off. So let's start with what we know up here. We have an exterior angle, we have this. We know that these two, the measure of angle 1 and the measure of angle 2 equal 180 because they are a linear pair. Or you can say that they form a straight angle or any of those things. But we know that these two guys together make 180, definitely, because they are on that. You and I also know that the measure of 2 and the measure of 3 and the measure of 4 equal 180 because the angle sum in a triangle is 180, right here, right? 2, 3, and 4 are in a triangle. Now notice these two equations have the same amount. When things equal each other, you can equal them to each other. So let's put this down here. So we would say the measure of 1 and 2, that's this part, equals 180, but that also equals 2 and 3 and 4. We call that a substitution. Now we're pretty close. Look at what we want. We want to show that the exterior angle 1 is equal to the remote angles 3 and 4. We've got some extra stuff, but guess what? It's the same extra stuff. We have a 2 here, an angle 2, and an angle 2 here. Let's subtract them from both sides. So we'd say the measure of angle 1 equals the measure of angle 3 and the measure of angle 4 added together because we did the addition subtraction property. And what that property lets us do is add and subtract things, and we subtracted this off of each side. This is known as the exterior angle theorem. Now, just quickly to show you how it works, this guy's so much fun. It can calculate some cool angles for you. So let's start with just a basic diagram. Here's our basic diagram. This is 70 and this is 45. And they want to know this. Well, yes, you could find this and then do this, but we also know that the exterior angle is equal to these two. So this must be 30 up here because together those add to 70. Let's show you another situation. If I had an isosceles here, and I knew that this was 30, again, I take 180 minus 30. Let's say I wanted to solve for this. So I take 180, subtract 30, that's 150, divide by 275. And now these two angles give me 105 as our answer over here. The exterior angle is equal to the sum of the two remotes. These three relationships will let you solve all kinds of cool interior triangle stuff that will get used in many units to come. Learn this stuff, it's great.